All right, folks. Let's do this. We just catch up from last lecture. We're trying to derive EK using principal virtual work, but first thing we need to do is try to figure out the displacement functions, because I mean, if we can figure that out for an element, then you can calculate string using theory of infinitesimal string. You can do stress, and then you can do internal virtual work. Yeah, that sounds great. But to actually do that, you've been following me on the matrix, class. Format is everything when you try to program this thing. So let's take a look at a simple case. Just try to shed some light on how this is gonna work for any element, both for matrix structural analysis or for finite element. It's the same basically. So yeah, let's look at this bar element. So it's undeformed, in its coordinates. You have the node number 1, node number 2, and then it's axial, right? So basically what you can do is that node 1 can move u1, whatever. Node 2 can move u2, whatever. They're independent. They can do whatever they want. So the question is, if I give you a point P on the undeformed coordinates, I tell you it's like xp. Can you give me like P is here, and now the P prime moves to, I don't know, maybe here. That's deformed. Can you tell me what this is if I tell you what U1 and U2 is? So yeah, you said, okay, well, you basically want a function which is a U, and then if I input xp here, it's gonna tell me the displacement of point P. Great. Okay, so how do I do that? It's not very apparent, but there's actually a couple of assumptions you need to make here. First of all, you could say, you know what? It looks like at 1, if I put in x equals 0, which is here, then the movement is u1, okay? And then if I put in, let's say this entire length is L. If I put in x equals to L, it should give me the movement for number 2, should be u2. So to do that, I can actually say, I can assume everything in between is just linear interpolation. So this has to be a linear function. What I know is that u at 0 equals to u1, and u at L equals to u2. So what I'm getting here is that I can assume ux equals to a1 plus a2x, and then I can do 2 equations based on this. So first of all is a1 plus a2 times 0 equals to u1. And then the second one is a1 plus a2 times L equals to u2. Well, so I can solve for a1 and a2. So what I got is a1 equals to u1, and a2 equals to what is it? A2 equals to actually u2 minus u1 over L. And then you can, plug it back in. Then you got your displacement function, x equals to u1 plus u2 minus u1 over lx. Yeah, if you're interested, you can check this. It works. Okay, it actually works. It works for every single point. If the movement inside it is kind of linear, you know. But yeah, this doesn't really help us much, because this, in the end, it is just a linear equation, and it has the linear components in there. u1, u2 are how much your nodal displacement is. So let's rewrite this. I'm not doing new math, but let's rewrite this. But this time what I want to do is I want to rearrange this equation so that I have all the terms associated with u1s together and all the terms associated with u2s together. So you're like, okay, that seems like a pretty trivial, but well, I'll do it. It becomes 1 minus x over L, and then times u1, so it's 1 and that, plus x over L times u2. Okay, I'm not doing anything fancy, or I'm not introducing anything new. All I'm doing is rearranging the terms so that I can group all the terms associated with u1 together and u2 together. And then I'm going to write this in matrix form. Okay, well, you're like, oh, matrix? No, I guess, yeah, probably not the matrix, but you know what I mean. I'm going to write it in a vector form. So the vector, the first component will be 1 minus x over, yeah. The second component is this guy. I'm using parentheses so that you are extremely clear. I'm not trying to add them or doing anything. I'm just writing this as a vector. It is not a vector of number. It is actually a vector of equation. Then times u1 and u2. And then I'm going to give these individual function components of this vector name, and I'm going to give this guy a name. I call it n1, and then I'm going to call this n2. So if I do that, you can rewrite this as just n1, n2 times here, you look at this. This is your displacement vector of your element, so it's just this. And a lot of time I would encourage you to always write it at the beginning, is to realize that n1, n2, they are not numbers. They are actually a function of x in this case. So basically what I did is I'm writing the scalar function of this guy. It becomes a n vector, which contains a lot of n functions, then times your delta. That's it. And then those n functions, they were called shape functions. But oh, okay, you're like, oh, that's a little bit too much. Okay, well, what does this all look like? Let me kind of summarize some facts about shape functions, and then you will be able to tell what they are. So basically, shape functions are associated with the nodes in your element. So basically, in this case, this element have two nodes. It'll have two shape functions. The physical meaning of a shape function corresponding to node let's say node I what is it? Okay, if you're looking physical, I always say, okay, we better take a look at what the shape function look like. Just using this as an example, the first N1 shape function, what does it look like? The N1 shape function here, if you would really draw it, x is 0 to L. If you draw it, what it looks like is that if, I don't know, why am I doing this? At x equals 0, it is 1. Then at x equals L, it's 0, and then it's a linear function. Without I kind of just telling you, you already know what we're getting at is for the shape function N2 is the opposite. When it equals to L, it's 1, and then it's 0 when it equals 0. So this will actually tell you the physical meaning of shape function is the displacement, we'll say profile of an element when the node I moves 1 while all other degree of freedoms are 0. So basically, if you just move the first node 1 and then keep number 2 0, this will be the displacement profile at the points inside that body, and then so vice versa. This is actually quite powerful observation. It does not just apply to this element. It applies to essentially all the elements. When you get to 2D or 3D elements, it'll be the function itself could be pretty crazy, but the basic idea is the same. So then the shape functions can be arranged into a n vector, and the n vector, which then times the delta vector, will give you ux in this case. Later on, we're gonna talk about beam. We're gonna actually there will be shape functions that you do that, it'll give you the displacement in the x or in the y direction and all that, but conceptually it's the same. So the beauty of this presentation is that if you think about a displacement function, you always think about a function. But when you think about a load or displacement vector, you're always thinking about numbers. But by doing this formulation, you are able to get all the kind of function, variable x, and everything into this shape function vector without worrying too much about it. And then those will just be unknown constant. The beauty is that later on we're gonna apply serial infinitesimal string. You're gonna do things like du dx or second derivative or all that type of stuff, right? But what you're really doing, if you look at this, because all the x terms are actually inside here, so this guy is constant. So du dx is simply becomes d of you just take a differentiation of each component within the shape function, and then times this formulation will never change. Okay, I would like to introduce another shape function about 2D beams, but I think that actually deserves its own lecture. But at least through this lecture, I want to hammer in your head that for an element, you can write out shape displacement function in terms of shape function times nodal displacement. Shape function times nodal displacement plus another shape function times nodal displacement, and then you can write it in vector multiplication term. And then finally, the physical meaning of shape function is simply, just let that degree freedom move one and see what your deformation inside your element look like. Then finally, when you take a differentiation of your displacement function, all you need to do is to take differentiation of your shape functions. This times the displacement vector thing, it'll never change. Alright, we'll see you next time.